All right, so here's the continuance of our Chapter 10 review. These are the spicier problems. Like I mentioned in the last one, we can't just square this to get rid of the root because it's not an equation. We'd have to do it to both sides. However, in the directions it says we want to turn this into something that looks more like this. A plus B times the root of C. So basically we want to get rid of this double root thing that's going on here, right? We're not going to be able to get rid of this root, right? Once it's an irrational number, it's kind of stuck as an irrational number. It's hard to make it rational again without changing the number. So this is what we want to do, and what that'll allow us to do is to create an equation. So we end up with this, and we want it to equal something that looks like this. Now, it's a good guess to guess that C is going to be 3, right? That root's just not going to go away. And what this allows us to do is to square both sides to get rid of the root. And when you do this, you have to be very careful. The tendency is to square everything individually, right? But that's not what squaring means, right? We have to take the entire thing and times it by itself. Squaring is just shorthand for that, right? So if you take the entire thing and times it by itself, yes, this root will go away because the entire thing is rooted. And if you were to distribute stuff out, you'd see that it would go away. But this does not just become a squared plus b squared times 3. There's some middle terms here. And I think if you write it out, you won't make that mistake. You'll see that we have to distribute. Cool. So this is what I have now. This I'm just going to keep the same, 61 minus 28 root 3. And over here, if I distribute, I'm going to get a times a, which is, of course, a squared. I'm also going to get a times b root 3, and it will be positive, so ab root 3. And you'll notice I'll get another one, right here. And that's what happens when you time something by itself. The middle thing, you'll always get the same thing twice, so I'll get 2 of those. And then, of course, to end up, I'll get b times b, which is b squared, and root 3 times root 3 is root 9. And, of course, the root of 9 is just 3. So this tells us that this part right here, and maybe I should highlight that. This part right here must be equal to this part. It's the only part with a root 3. And it also tells us that this part right here, the only rational part, is probably going to come from these guys, right? So I'm going to write that out. I know 61 must equal a squared plus 3b squared. And I know that this part, negative 28 root 3, must equal 2ab root 3. So these are kind of my system of equations, so to speak, here. And we're going to solve this not using sub or elimination. We're just going to kind of use our brains here. This right here seems kind of obvious, right? What times 2 gets you negative 28? Well, negative 14. So we know a times b must be equal to negative 14, right? We've already got the root 3 here. And if we times negative 14 by 2, we'll get negative 28. So a times b must be negative 14. That'll limit our options for what a and b could be. And if it works for both of them, then we win, right? So let's list our options for a and b. There aren't that many ways to multiply to negative 14. I'll list them over here. So our options, if we're multiplying to negative 14, are 1 and negative 14, negative 1 and positive 14. We can also do the reverse of that, but I'll get to that in a second. 2 times negative 7 would get the job done, right? They multiply to negative 14, and so would negative 2 times positive 7. Now, as I said earlier, we can reverse these, because it doesn't matter what order a and b are in, right? So a could also be 14, and b could be negative 1. A could be negative 14, b positive 1. A could be 7, b could be negative 2. A could be negative 7, and b could be positive 2. So we have quite a few options if you think about reversing these. However, by looking at this problem, this is going to get pretty big, right? So imagine I chose these guys, right? A squared is pretty small, and then I square 14 and times it by 3. That's going to be way too big to get to 61. Same thing here. A is really small, B is really big when we square it, right? A is small, B is big, A is small, B is big. So we know right off the bat, none of these are going to work. It's got to be where A is bigger than B. So these are the ones we want to try. So let's think about that. So 61 equals a squared plus 3b squared. Well, if a is 14, we get 196. And if b is -1, we get positive 1 times 3, which is 3. So this isn't going to work. 196 plus 3, it's too big. We're going to have the same issue here, right? Because the positive signs aren't going to matter. Positive and negative isn't going to matter because once we square them, they're all going to come out positive, right? Just like this did. So if that didn't work, this won't work either. So it's got to be 7, -2, -2, and 7. Let's check those. So if a is 7, we get 49. And if negative b is, sorry, let me say again. If b is a -2, we get positive 4 times 3, which is 12. And that works, right? 49 plus 12 is 61. So this definitely works. 7 and -2 for A and B. And as we discussed earlier, right, the minus signs, where they are doesn't really matter because we're squaring everything. So this should work too, and let's prove that, right? -7 squared is 49, and 2 squared is still 4. 4 times 3 is 12. So both of these work. And whenever we have multiple solutions, we should always ask ourselves, does it really work with the original problem, right? We've changed things a bit. We squared both sides. When you square both sides, you're bound to have answers that work after you square, but not before. So if we go back to the original problem, we can check our work and see which of these actually works. So always check for that. I think in this one, we will have an extraneous solution. So here's what we originally had. And we're saying that this could be equal to an a value of 7 and a b value of -2 with c being √3. Or it could be equal to -7 plus 2 √3. And here's where you need to be able to estimate in your head to be able to check these answers. Because one of these makes sense and the other just definitely doesn't. So if we do this, right? √3 is smaller than 2, right? √4 is 2, so this is smaller than 2. If it were exactly 2, and we know it's smaller than 2, but if it was exactly 2, we'd get 56 here, right? 28 times 2 is 56, and we get a positive answer inside the root. So our answer is positive inside this root because that's smaller than 2, so it's not going to get close to 61. Cool. So over here, we have 7 minus 2 √3 and -7 plus 2 √3. And which of these is going to come out positive? In other words, is this bigger than 7? If it is, then this will come out negative, right? We'll be taking away more from 7 than we actually have. And then this one, right, if it's more than 7, then good, awesome, this will come out positive. So the question is, how big is 2 √3? Well, if √3, again, I'm using my estimation skills here, was actually a √4, it'd be equal to 2, right? 2 times -2 would get us -4, and 7 minus 4 would come out positive. So that would be our answer. We know this isn't quite √4. I mean, it's √3, right? So it's going to be 1 and change. And 1 and change times 2 is about 4. But again, it's still smaller than 7. So this would come out positive. So that looks pretty good to me. If we check this one, right? If this comes out to 2 times, 1 point something. If we do that, we're going to get close to 4. It's going to be 3 and change, right? At most. When we do that, we're going to get a negative answer. And that is not what we have here. We already said that this will come out positive. So this cannot be the right solution. 7 minus 2 √3 must be. We call these solutions that pop up when we do a little bit of algebra extraneous solutions if they pop up and they end up not being true. And it's because some of the manipulations we did to the problem actually changed the problem slightly. That's why squaring and rooting is so dangerous on both sides. It kind of actually changes the problem. It's not literally the same equation after you do that. And so you have to look for these issues. Okay, cool. So that's 10-4-5. Pretty spicy. Let's move it on over to 10-4-6. And we will need a separate sheet of paper for this because as you can see, there are a lot of words. So let's zoom out so you can start reading. So it says... yeah, there we go. Mary's Trinket Shop sells bracelets for $10 each. They sell 50 bracelets a week for a total revenue of $500 per week. Okay, cool. So they want to increase their total revenue to exactly $600 per week. Apparently they need $600 exactly. The question is, how are we going to change the price, right? So they will sell 2 fewer bracelets per week for every dollar that they increase the price. So in other words, if you raise the price, fewer people are going to buy, right? It's going to be too expensive. And so they calculated that if they raise it $1, then instead of selling 50 a week, they're actually going to sell 48. So it'll be 11 times 48 for their revenue. And if they raise it $2, it'll be $12 a bracelet. They'll have lost 4 customers buying bracelets, so they'll get 12 times 46. So they want it to be exactly $600. The question is, what are the possible prices they could make the bracelets where they get exactly $600 a week? So this is a tough question, and I spent some time thinking about it with myself, and the main principles of problem solving apply here. So first off, what do we want to know? We want to know how much we can increase the price by. So the question is, how much can we increase, right? I'm going to do a little I like this. That's going to be our variable, and I'm going to label it. So amount increased. And this is going to apply to the price, and it's going to apply to the bracelets, right? Because the more we increase the price, the less bracelets we'll sell. So we know the initial price was 10, right? And so how much we increase it by will be 10 plus that I. That'll be the new amount that we're selling them for, right? The amount we started with plus how much we're increasing. And of course, we'll take how much money we're selling them for, right? That's going to be our overall price. And we'll times it by how many we sell to get our revenue. And we want our revenue to be exactly $600. Now, initially, we were selling for 10, and our price was 10, and we were selling 50 a week, right? And so they're saying if we don't increase at all, we'll get 10 times 50, and that'll equal 500, right? So the question is, how much can we increase this by so that we end up with 600? Well, every time we increase it by $1, right, increase it by 1, this goes down by 2. So this is going to get smaller every time we go by I. Now I'm going to leave it like this for a second and have you think, right? If I add $1 onto the price, am I going to lose 1 bracelet? No, right? I'm going to lose twice as many bracelets as I increase per dollar. So if I increase it by 1, this should be minus 2. If I increase it by 2, this should be minus 4. So in other words, it's always double whatever we increase it by. That's how much we're losing in sales, right? People coming in and buying stuff. So again, the idea is we're adding on a certain amount, and for every dollar we increase by, we're going to lose 2 bracelets sold, and we want that to be $600. And once we have this set up, it's kind of obvious what's going on here, right? We took price times the number of bracelets, right? Here's our price, and times the number of bracelets sold per week. And that gets us our revenue per week. And of course, this looks like 2 different variables, right? Price and bracelets, right? How many bracelets you're selling, what the price is. But of course, they have a relationship. And what's that relationship? It's how much you increase the price by, right? If you increase the price, it's going to affect the price of the bracelets. And here's how we can represent that. So instead of having P and B be our 2 different variables, we can represent it like this. And this is a big brain thing, right? Always make a variable of the thing you want to know, and try to find the relationships between the other things that are happening in the problem, right? The price versus the bracelet sold. And here is that relationship. Cool, we know that times together will get us our revenue per week. So now we solve, and if we distribute, we're going to get a quadratic, right? So 10 times 50 is 500. And 10 times negative 2i is negative 20i. And of course, 50 times I is going to get us plus 50i. When we do I times negative 2i, we'll end up with negative 2i squared. And of course, this needs to equal $600. Cool. From there, if we get our i's together and simplify and make this not negative, life will be good. So I'll just write it out first like this with this as our leading term. This is our linear term. It's going to come out to positive 30i. And then this is positive 500. And that's going to equal 600. If I subtract this over, we'll get negative 100 there. And because the leading term, this one right here, is negative, what I'll end up doing is I'll times everything by negative 1 to make this equation a little bit easier to look at. So we get 2i squared minus 30i plus 100 equals 0. And from here, it's actually pretty easy to factor, right? You can divide everything by 2 if you want, and you'll get I squared minus 15i plus 50. But honestly, it might have been easier to solve like this. Just, 2i times I is what you would need. It's really just kind of up to you. When we get here, we need numbers that multiply to 50 and add to negative 15. So they've got to be double negative so that they'll add to a negative 15i, and they'll still multiply to a positive 50. So we need 5 and 10, yeah? So that means our increase amount could be 5, or it could be 10 for I. Now, this is not our answer because they want to know how much we can sell them for, right? The two values. Well, if the original price was 10 and our increase is 5, then we can sell for our new price at $15, and that'll get us exactly 600 bracelets, assuming we're right about, every dollar we increase by, we'll get 2 less sales. The other price, if it starts at 10 and our increase is 10, is 20. So either of these values will work. Okay. So there's Marie's Trinket Shop. That one's very tricky, but again, it's based on the principle of trying to have as few variables as possible and always try to see the relationships between them, and of course always write down a variable of what you want to know. And we wanted to know the price increase. All right, cool. So for this one, looks awful, but it's not. First thing you notice is probably there's fractions, right? So how do we get rid of fractions? Well, if we multiply by x squared, that will divide out to 1, and then it'll go away, right? So let's do that to every term, because of course if we multiply by x squared to one thing, we should multiply x squared to every term. Otherwise it's a different problem. And while this divided out to 1, anything divided by itself is 1, this does not divide out to 1, right? X squared divided by x just becomes a single x, right? And so our new equation is going to be 10 times 1, which is just 10, plus 22 times x, because the x is divided out, 1x was left, and then we get 4 times x squared, which is this, and x squared times 0 is 0. If I rearrange this is a pretty easy problem. I'm not switching anything from side to side, so I don't need to subtract or add. I'm just rearranging. And from here, you can notice everything's divisible by 2. So if I divide everything by 2, I get x squared plus 11x plus 5 equals 0. And factoring this to solve is pretty simple. I need numbers that multiply to 5 and add to 11. Did I goof here? Multiply to 5, add to 11, 5 and 1. Yeah, I'm off by something. Where'd I goof? Perhaps this one is not factorable. So perhaps instead what we need to do is think what kind of roots we could use. Yeah, that's a little bit harder than I thought it would be. Oh, I know why. This should be a 2. There we go. Right? Dividing everything by 2 is going to put a 2 there. So we'll need 2x and x. That makes things a little bit better. That means if I put a plus 5 here, I'll actually get 10 x's and plus 1 for an x. I thought we were going to get an unfactorable equation. We had to use roots to solve it. From here, the answers are pretty easy. The first one is negative 5, I would say, right? Negative 5 makes this 0, and it makes this not 0, but 0 times anything is 0. Or our other option for x is actually negative 1/2. And that's because if you plug this in here, it says divide by 2, right? 2 divides by 2, and we get negative 1. Negative 1 plus 1 is 0. And while that doesn't make this 0, it will make that. So 0 times anything is 0. There are both our answers. That was almost a much more interesting problem. This one I actually think is one of the easiest hard ones, quote unquote, that we've done so far. As long as you don't make a calculation error. All right, for this one, this doesn't look like a quadratic, but it is. Once again, we see fractions. So what I'm going to do is I'm going to times by the quantity of x minus 5, and I'm going to do it to every term. That's a term, that's a term. These divide out, which is why I did it, right? Now, in order to get rid of this fraction, I'm going to times everything by x minus 2 as well. The quantity, because it's 2 terms, right? And that divides these out. And so what we end up with is x minus 2 times x minus 6. These both divided out. And then we get 4 times the quantity of x minus 5 because these both divided out. And this just gets rid of our fractions and makes our life a little bit easier. From here, if we distribute, we're going to get a quadratic, right? So let's do that so we can get a nice quadratic. X squared is what we get here. And then, of course, if we distribute that, we get negative 6x minus 2x plus 12. and then this will be 4x minus 20. And we've done a lot of distributing, so I just want to stop for a second and talk about why I knew distribution would probably be a good idea here. Well, 2 might make this equal 0, right? It's nice and factored over here. And if I make that 0, who cares what this is? I get this to equal 0. But you'll notice if I plug in 2 over here, I get 2 minus 5, which is negative 3. And 4 times negative 3 is not 0. So making this 0 over here doesn't solve the problem because we actually need it to equal the same thing on this side. So it's kind of hard to tell what number is going to make both sides equal. I wish this equaled 0 altogether. So what I'm going to do is I'm going to distribute and get to 1 quadratic. Now that I've got this, I'll have everything subtracted or added over here to make this whole thing equal 0. And then I can start thinking what multiplies to make 0. So if I subtract 4 x's, I already have an x squared. If I subtract 4 x's, I'm now subtracting negative 6 x's, negative 2 x's, and negative 4 x's. It's going to be a total of negative 12 x's. And if I add 20 to both sides, I'll end up with 32 here. So let's see if this factors. Well, in order for this to multiply to a positive, I need the same sign for both, right? So I think I'll need double negative. That way it adds to a negative 12 for my total number of x's. Well, 32 has a couple options, right? 32 and 1, 2 and 16, but I think 8 and 4 are what I'm going to need. Because notice I'll get negative 4x's and negative 8x's for a total of negative 12. And I'll also get positive 32 for my constant. So our two answers are 8 or 4. Okay, so that will conclude our review, all the questions you guys had. The next video will be on chapter 11 for the few exercises you have.